I want to do a quick intro video on area and polar. Most of our work will be done together in class because the best way to do this is just to practice. So this video will be kind of quick, just giving you the general idea before we get back together again in class. So when you're talking about area and polar, I have this little picture that I drew several years ago, and I kind of hand drew it because it was hard to do with any sort of technology. When you're finding area, so you have this and you have this shaded region right here, you need to know where we start and stop. But it's different than rectangular coordinates where it's just like from your x to your x or from your y to your y. This is going to be from a radial line to a radial line. So here you think of it almost like the hands of a clock moving, although it's going counterclockwise, where we start our area at this radial line that I called alpha, and then we stop our area when we get to this radial line that I called beta. So those are going to be your boundaries of integration. So if you look at the definition of area, first it says it has to be a continuous function on this interval from alpha to beta. And this 0 less than beta minus a less than or equal to 2 pi basically means you can only go, the most you can go around the circle is 1 full revolution, 2 pi. So it can't be a situation where you kind of like retracing your steps. Then your area is going to be between radial line alpha and radial line beta. You'll notice those are your boundaries of integration. And the formula we use to find area is going to be 1/2, and it's always a half. It actually comes more from like circular definitions. The integral from alpha to beta of your function of theta squared. So you have to be given what your function is. So they have to say r equals cosine or r equals 2 plus 5 cosine, something like that. So your formula, and this is the one formula that you do need to commit to memory. Obviously, when you do a quiz for me, you'll be using your notes, but on the AP test, this is one formula that you'll need, is how to find polar area. And it is always 1/2 the integral from the starting angle to the ending angle, those are your alpha and beta, of your function of theta being squared. The biggest challenge in these problems are figuring out the boundaries, figuring out where the area starts and stops. If you're allowed to use a calculator, the calculator can definitely help because you can go into your mode and change your theta values, and you can kind of see what's formed. So you do kind of have that as a backup plan. If you're not allowed to use a calculator, often they give you a lot more information, more of a picture. So I just want to do one on this video before we get back together in class. One of the most common areas that they're going to ask you to find are areas of petals, of rose curves. They're actually my favorite area to find as well. So this one has a rose curve given by 3 cosine 3 theta. We talked on Tuesday that if your coefficient of your angle is odd, it's this number of petals, and if it's even, it's double that number. So this one has a 3 in front of the theta. So my petals, there are 3 of them. The number in front, the coefficient in the beginning, tells you how long the petals are. Not that any of that really comes into play too much with this. So the first thing you want to do is you need to figure out, where does these petals start and stop? So I'm just going to pick the petal that's in the first quadrant. I need to figure out, what are these radial lines? And they're going to come from the pole. They're going to kind of originate at the pole. The way I do that is I do something that I talked about earlier in the week called find a tangent line at the pole. A tangent line at the pole means, when does your original function equal 0? So where does it like originate from that 0, from that pole position? Divide by 3, I get just 0. So it wants to know, when does the cosine of 3 pi equal 0? Well, I need to know when cosine equals 0. And cosine equals 0 at cosine equals 0 at pi over 2. So that means if I set 3 theta equal to pi over 2, divide both sides by 3, my angle measurement is pi over 6. Now that's going to be this one. Now here's the nice thing. You're going to have so much symmetry in these graphs. That means that down here, this must be negative pi over 6. Another option with symmetry is, instead of going from negative pi over 6 to pi over 6, you could also go from 0, which is the polar axis, to pi over 6, and then double your answer. So you'll see a lot of times where I'm going to mention symmetry with these. So again, you could go 1/2 the integral from negative pi over 6 to positive pi over 6 of your radius, your r equation squared. So that's one correct setup. Or you could say, well, I'm going to double. So 2 times a half, and I'm going to only go from 0 to pi over 6. We call it like a half petal. And you'll actually see some on Delta Math that talk about half petals. And then go 3 cosine 3 theta being squared. So that's your setup. To finish these, I'm not going to have you do any of these by hand. You are going to use your calculator. It does not matter if you're in polar mode or not. That won't change anything. What does matter is that you have to be in radian mode because of all the trig. So you should be if you double check you're in radian mode. So I'm going to go to Math 9. I'm going to do the one with the symmetry. So I'm going to go from 0 to pi over 6. I'm going to put an extra parenthesis so I can put this entire 3 cosine 3 theta. Make sure you square the whole thing and not just the angle. And I'm going to get that answer, and then I'm going to multiply by 2.5, and those actually cancel each other out. And we end up getting an answer of 2.356. If they ask you for the entire area, it's truly just a matter of taking that answer and multiplying by how many petals there are. So if I know that one petal is 2.356, then this entire rose curve has 3 petals, so I would multiply by 3. So really any rose curve problem, whether they're asking you to find half a petal, a full petal, or all of the petals, it's all going to come down to starting with that basic, because of the symmetry, that basic piece, and then multiplying if they want the full area. So that's a rose curve example. So that gives you kind of the basics. We'll get back together and we'll do some other examples, but it's a nice one to start with.